PowerPoint presentation as well?
Yes, sir.
Okay, fine, very good. So yesterday we were discussing this Lennard zone potentials and how Lennard zone potentials actually comes into play, and what is the mechanism of attractive interaction in Lennard zone potential. So this we have done yesterday, how dipole-dipole interaction leads to this attractive term in Lennard zone potential, and how Pauli's exclusion principle can lead to this kind of term, which leads to the repulsion. Okay, so I had given you one exercise yesterday that okay, you had to obtain the value of r at which we should see minima of this curve. Have you done that exercise? And okay, at what value of r we find out the minimum value of the potential? Have you done? What is the condition? R by sigma is equal to 1.12. Very good, Harish. So actually what you have to do is you have to take derivative of u with respect to r, and for minimum you have to put that derivative to be equal to 0. And then when you simplify, you can find out that the condition at which minimum occurs actually is r over sigma is equal to 2 raised to the power 6, which is roughly like 1.12. I hope every one of you have been able to do this. In case anyone faced a problem with getting this expression, you can let me know so that I can help you out. Anyone face a problem in getting this? If yes, please let me know. No. Okay, Ankush says no. I hope everyone, that's quite simple. Okay, fine, no problem. So the value of u, you will notice from this expression even, that when you put r over sigma is equal to 2 raised to the power 1 by 6, what should be the value of u at that particular point? Minimum point, I mean, what will be the minimum energy? That is going to be minus epsilon, or minus this one. You can try that. That's a fairly simple thing again. You have to put r over sigma is nothing but 2 raised to power 1 by 6. So you have to put, this is like 1 over 2 raised to power 1 by 6 whole raised to the power 12. So this is like 1 by 4 minus 1 by 2. You simplify them. You take 4 as an LCM, I think, and then rearrange the things. You should find out that finally u at r is equal to, let me say, r naught, comes out to be equal to minus epsilon. Okay, so what is the and you can also prove that u actually is equal to 0 when r is sigma. That's straightforward. When r is sigma, this term is 1, this term is also 1, so both subtracted from each other gives you 0. So r equal to sigma is a point where the potential is 0. I mean, attractive term is exactly the potential due to attractive part is same as the potential due to repulsion. And so physical meaning is, what is sigma? Sigma is related to range of this interaction, you can say, isn't it? Sigma can be related to range of interaction. So we can say, okay, whenever r is equal to 2 raised to the power 1 by 6 sigma, then we say the Lennard zone potential is minimum. Or you can say when r is 1.12 sigma, then this potential refers to the minima. But this minima is there for only two particle interaction. I mean, pair potential. Pair potential means we are talking of only a pair of particles. We don't bother about many body problem. If we have so many particles, because in ideal gas, means in ideal practical gas, there are so many particles. There things will be little different. We will be seeing that also. But it is the formula which has been obtained for a pair of particles. Suppose you have only two dipoles. This model came from only a two dipole arrangement. So those two dipoles, when interacting with each other, leads to this form of potential. Now, if we try to see these numbers for various noble gas atoms, then you can find out that, okay, I mean, epsilon is something like this is potential, so it is in ergs, 10 to the minus 16 ergs. They have followed some erg unit. So this is 14. Let us try to pay attention to the numbers. So this is 14. This is 50. 167 means as the size of the noble gas atom increases, the potential energy or the magnitude or extent of interaction, attractive interaction increases. Means this well, we can see this to be like a potential well. So this well will be deeper for xenon and shallower for helium or neon. And the depth of the well keeps on, potential well keeps on increasing while we go towards xenon. And this can be explained on the basis that xenon atom being larger in size is easier to deviate from its spherical distribution of charges, and then that is what makes this dipole moments more and more pronounced in case of larger size atoms, and hence the interaction or rather Lennard-Jones interaction or this attractive part will be more stronger, and hence deeper will be the well. Similarly, this sigma, now you can compare sigma also can be related something like size of the atom, you can say what is the range. So this increases as well. So these are the values of sigma and epsilon for Lennard-Jones potential for various elements in the noble gas block. So you should note these values. I mean, in case you want to do some calculations regarding noble gas atoms, then we can use this kind of potential and these parameters, and hence then you can proceed with the calculations further, because this Lennard-Jones potential are very much used in molecular dynamics, where we try to calculate properties of the atoms, many atoms in a system, and then the potential between them is described with this kind of formula. Well, I mean, once we have done the pair potential thing, I mean, we have obtained the potential of interaction between gas molecules, then let us try to calculate the lattice constant. Now, since we are not discussing one pair of particles, means only two atoms of noble gas, we are not discussing that, but we actually want to understand the crystals of noble gas. So crystals of noble gas means we have so many atoms brought together to interact in some small volume, and that's what lead to crystal formation. So now we want to see that, okay, if there are so many atoms of noble gas, then they are interacting with each other, what kind of crystals they can form, and what will be the lattice constant. So we want to actually obtain the expression for lattice constant here. So if total energy, I mean, this is the energy for any pair of the particles. This is the energy for one single pair of the particles. So what will be the total energy? Oh, Sandeep. Okay. What will be the total energy? Total energy will be summation over the energies of each pair. So that's what has been done here. I hope you have done it somewhere in your earlier classes. So suppose 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 we have a system of three particles. Sorry, I didn't put what you call I didn't put the detailed formula here, how we obtained this, because I assume that you have done this, but okay, let us give a quick oral attempt to understand this basically. So basically total energy, if you have to write down, that is equal to nothing but summation of potential energies for different pairs. Suppose we have a system of three particles. Let us name, you draw any three particles in your notebook, name them 1, 2, 3. Okay, So what will be the total energy? Total energy will be coming from interaction of various pairs. We are just talking about pair potential or two body interaction. So what will be the total energy? Total energy will be, say, suppose potential energy of pair 1, 2 plus potential energy of pair 2, 1. Or I mean, 1, 2 and 2, 1 will be giving the same. So we don't need to count it two times. So 1, 2, first is interacting with second, then first is also interacting with third. So second term will be V13. Then second, there will be third term called in relating to the interaction of second and third particle. So V23. So there will be altogether three terms. And but this summation actually, why this half is here? Because this summation is something like, okay, summation over J not equal to I. So this prime is representing J not equal to I. So we are taking all pairs, and where J is going from 1 to n, then I is also going from 1 to n under the condition, suppose there are n particles in the system, then under the condition that J is not equal to I. If J is equal to I means particle is interacting with itself, which is not there. Physically, it is not there. So that is self-interaction. So we can get rid of that. Plus, what we are saying here is, in this summation, actually, there are two terms. One term is coming from Vij, other is coming from Vji, because there is no restriction. We are not saying I greater than J. So if we are doing so, then we are counting each term two times. For example, V12 and V21. Both terms will appear, but it's like a double counting. So that is why this factor of half is sitting here. Okay, so this is giving you the total potential energy for a system of n atoms of noble gas interacting with each other, and where R now is not this R. I mean, it's not like that, but we are referring this interparticle separation in terms of nearest neighbor distance, small r. So now here, I mean, what we are saying, this r is not this one, but it is just nearest neighbor distance. So then what distance between the reference sign I and j, this P, this is the total, I mean, Pij into r is the total distance between I and j. And what is r is nearest neighbor distance. That's what I told you just now. Okay. For BCC, sorry, for FCC, because most of the noble gas crystals form FCC crystals, so there will be 12 nearest neighbors for a FCC case. And in this, then, what does it mean is, if we take sigma over r common outside, then there will be what you can call 12 neighbors. So there will be a factor of 12. I mean, there will be a factor of 12. Each neighbor giving a value of 1. Why this? I mean, okay, let me come to the next slide. There I have given this. So then we will discuss this. So suppose this is representing a FCC case. This is representing FCC arrangement of atoms. Then this is nearest neighbor, isn't it? For this atom, this is the nearest neighbor. So we choose any reference, say I, and then how many such neighbors are there? In one particular plane, there are 4, right? But then there are 4 others to the upward plane, because this is a 3D structure, right? So there is another layer above this, I mean above the screen, and then towards that face, so there will be a atom sitting exactly at I would say half a/2 distance along this direction. So that is also going to be at exactly same distance as that of this one. So there will be 4 such, one sitting here, other sitting here, other here, other here. So 4 upwards, 4 downwards. So 4, 4, 4, 12, total 12 neighbors. So in that term, what we will be getting, then you will be having next nearer neighbor, which will be having a distance of r by √2. Then next to next nearest neighbor, that will be having something. I mean, interesting thing is, I missed it. I did something wrong here, because this can't be r by √2. isn't it? There is something wrong. This should be root 2 r, not r by root 2. I mean, it's a simple thing. I mean, we have to find out this distance, right? This distance and this distance is same. So if I complete this triangle, then this is suppose x by 2, this is also x by 2, then this is also x by 2. So you apply simple Pythagoras theorem. So what will this give you? This distance is r by root 2 up to this. Okay. But this distance is twice the this one. So this will be total root 2r. I'm sorry, there is a error here. So this will be root 2r and so on. Then this one will be little larger than this, obviously. This is root 2r. This will be larger than that. So other will be definitely larger. Somewhere you may find 2r. So now let's come back to this one. So the values of Pij, that's what it means. I mean, value of Pij for nearest neighbor is 1. Then Pij for nearest neighbor is 1. Okay, because in that case, the distance is just equal to 1 times r, nearest neighbor distance. So in that case, what will be the value for this? How many terms will be appearing to the nearest neighbor? 12 terms. So there will be 12 terms here sitting in this summation. So each one of them will be giving 1 plus 1 plus 1 plus 1, 12. Okay. So this will be giving you 12. Same is the case here. I mean, Pij is 1 for nearest neighbor. So, okay. So you have to be a little careful. Sorry. So this will be, I mean, 12 into 1 sigma you can take outside, okay. Or sigma by r raised to the power 12 you can take outside. So sigma by r raised to the power 12 taken outside. Okay, let's do it in notebook. I'm sorry. You do it in your notebook. Let me do it in my rough paper I'm sitting with. So let us take sigma by r raised to the power 12 directly, like, okay. So what you will be left with this inside the summation over j prime, you will be having 1 raised to the power 12, and there will be 12 such terms for nearest neighbors. So this will be like 12 into sigma by r raised to the power 12, okay, minus again 12 into sigma by r raised to the power 6. This second term will give you, of course, there will be another 12 terms corresponding to this. So 12 into sigma by r raised to the power 6. Then plus higher order terms, there will be Pij for next nearest neighbors will be root 2r. I hope you remember this one here. This will be root 2r for next nearest neighbor. How many next nearest neighbors are there? 1, 2, 3, 4. Again, I think they are going to be 12 in number. You can check this. They will be 12 in number or so. But then this term will contribute very less. Why this term will contribute less? Because you will have sigma over root 2r raised to the power 12. So now let us take sigma over r raised to the power 12 common. So you will be getting 1 by root 2 raised to the power 12. And root 2 is sitting in the denominator. So root 2 raised to the power 12. Can you imagine? This is 2 raised to the power 6. 1 by 2 raised to the power 6, which is something like 1 by 64. Okay, so this will be like 1 by 64. That's why this series converges to something like, for a case of FCC, okay, I mean, the nearest neighbor contributes to the most of the interaction energy of the inert gas crystal. The corresponding sum for HCP, this will turn out to be equal to, for HCP and FCC. I hope you remember that we had discussed in one of our lectures that HCP and FCC structures are identical. in a sense that both are 2D hexagonally stacked layers. I mean 2D hexagonal layers stacked in specific order. So for HCP, it is AB, AB, AB type of stacking. For FCC, it is ABC, ABC type of stacking. And interestingly, in both cases, the number of nearest neighbor is 12 only. Okay. So this term, if you take 12 common, I mean, if I simplify this, okay, sigma over r raised to the power 12 minus sigma over r raised to the power 6. This will be like r raised to the power 12. Okay, just a minute. Okay, so I mean, if we take sigma over r raised to the power 12 common, so summation will give you a factor of 12. That's what is the main thing. And if you use this summation further to the next nearest neighbor, next to next nearest neighbor, you will be finding terms which are very small. One of the term I retained for next neighbors, next nearest neighbors, that was 1 by 64. So you can imagine that is going to be small. Next term is going to be further smaller. So interesting thing is that this long series, of course, there will be infinite many atoms in a, I mean, very large number of atoms, large number of neighbors for a reference atom. But then that series will converge close to 12. For HCP, this value comes out to be 12 point something. For first summation and second summation, it comes out to be equal to 14.45. Because here, now you should see, here the power is raised to the power 12. So 1 by root 2 raised to the power 12 will be like, say, 1 over 64. This series will converge very fast rather than this series. This is 1 over root 2 raised to the power 6. So 1 over 2 raised to root 2 raised to the power 6 will be like 2 raised to the power 3. So this will be 1 by 8. So that is why this series converges to rather 14 or close to 14, but this will converge very fast and very close to 12. I don't know if you are able to make out what I'm saying or not. Is this okay or not? I mean, can you get what I'm saying?
No, sir.
Huh?
No, sir.
No. So what is the thing you are not getting? Can you please ask any question?
Sir, actually, when we put Pij in the summation, then how factor of 12 comes?
This summation is running over all the neighbors. This is like a pair potential. Okay. I can't write anything on this screen now, unfortunately, but okay. You follow my words. I will surely help you. Total potential energy U is equal to summation over I and summation over J, isn't it? It is like this. And Uij, let us say two particle interaction potential is written by Uij. This one, Uij, right? So total potential energy is summation over I, summation over J, Uij. Means you have to sum over the potential of sum over the interaction potential of all the pairs. This is what it means. Suppose we say we have a system of 3 particles. That's what I tried to tell you in the beginning. Then your I can run from 1 to 3 and J can also run from 1 to 3 under the condition that I is not equal to J. Is that clear up to this?
Yes, sir.
Okay, so what will that be? These are two summations, summation over I and summation over J. So let me put I is equal to 1 and in summation, second summation, J will go from 2 to 3 because I can't be equal to J. So what will be the total sum or total terms? So it will be like U, I is 1, J is 2. So U1 2 plus U1 3. There will be only 2 terms. Correct? Plus, when I is equal to 2, what will that give? U2 1. U2 is not there, forbidden because self-interaction. U2 3. Similarly, you will be having U I is equal to 3 now. So I31, U31 plus U32. U33 is forbidden. So that's it, right? But this is the case of only 3. And then of course there is a double counting. So that's why we have kept this factor of half here, because double counting is not physical. Fine. Now it is the case very simple of 3 particles only. Now when you have large number of particles, we are talking now of a crystal. Let's come here to the next slide. Maybe this will help you. So now let us say this is my reference element, reference atom. Now if I have to write down the potential energy, what will that be? There will be one term. So let me name this as 1, central atom, reference atom as 1. Let me name these 4 as 1, 2, 3, 4, right?
Yes, sir.
So there will be another 4 in the plane above this one. So one will be sitting here, cross. I'm saying let's just draw cross here. But that will not be in the same plane. It will be at, I think, a by 2 distance along this direction, right? There will be 4. So how will be this summation going to? So what will nearest neighbors give you? So this is 1, this is 2, 3, 4, 5. Then what will that be? U 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. And then 4 will be downwards. So 1, 10, 1, 11, 1, 12, 1, 13. So total there will be 12 pairs. Is it clear?
Yes, sir.
And all these 12 pairs, interestingly, are identical. All of them are sitting at the same distance. That is why these are called nearest neighbors. So each nearest neighbor will give you what? I mean, if we take sigma over r common outside, sigma over r raised to the power 12, let us take that common outside the summation for first 12 terms, not for everything. Or even you can take it common throughout. Sigma over r raised to the power 12. Let us take it outside summation. We can take it outside summation.
Yes, sir.
Because it is going to sit with every term.
Yes, sir.
And accordingly, the summation is left only for summation over I and summation over j, 1 over pij, isn't it?
Yes, sir.
Raised to the power 12, not just 1 over pij, but 1 over pij raised to the power 12. And what is pij for nearest neighbor? It is 1. For nearest neighbor, pij is 1. Now you see, pij into r is the distance between ith atom and jth atom. But for nearest neighbor, what will be this? R only. For next neighbor, next to nearest one, this will be pij will be root 2. But for nearest neighbor, pij will be 1. So it will be like 1 by 1 raised to the power 12. Right? But there will be 12 terms. Not because of this 12, but because there are 12 nearest neighbors. So if you expand this summation, this will be 1 over P12 raised to the power 12 plus 1 over P13 raised to the power 12 plus 1 over P14 raised to the power 12 and all the way up to 1 over P113 raised to the power 12. But for all up to all those first 13 neighbors, Pij is 1 because all of them are nearest neighbors. So what will that summation give us? A factor of 12. Right?
Yes, sir.
I am talking of first term as of now. Then you move to next neighbors, next nearest neighbors. So these are the next nearest neighbors. Sorry, this is not by root 2. This is root 2r. This is under root 2r. So Pij now is under root 2.
Yes, sir.
How many next nearest neighbors? Again, we can count. Okay, I mean, there is one in this point, other one here. There is one going to sit here, 3, 4. There will be 12, I think, again here. I mean, 4 in this plane, 4 in plane upwards, 4 in plane downwards, I think. There will be 12 again. But that 12 into, what is the summation going to give you now? 1 over Pij. So it is something like P114, right? Because n we are varying now. We went to 14th. That is not nearest one now. This is next nearest. So this will be root 2. So 1 by root 2 raised to the power 12.
Yes, sir.
Isn't it?
Yes, sir.
So 1 by root 2 raised to the power 12 is 1 by 2 raised to the power 6, which is 1 by 64, I think.
Yes, sir.
So if you take this for 12 neighbors, this number is going to be very small. I mean 12 by 64, I think, isn't it?
Yes, sir.
12 by 64 it is, because if there are 12 next nearest neighbors, then there will be 12 terms, which is exactly same, 1 by 64, all of them giving. Then 12 by 164. I think this gives you 4 3s are 12, 4 1 2 4 6, something like 3 by 16, I think, which is a number very less in comparison to 1. If I do a quick calculation, let's do directly. Okay, 12 by 64, 0.1875. So what will next nearest neighbors give to this series? So it will be like 12 from nearest neighbors plus 0 point something, it is coming, it is 187. Okay, then you move to next nearest neighbors. Now these are going to be farther away. What is next nearest neighbor is this one now, next to next. This distance is larger, so the factor here is going to be further larger. I didn't put the factor exactly, but that is going to be larger. So the contribution of this term will be further very small, isn't it?
Yes, sir.
So altogether, what is the message of the story is that for HCP case, the first term will be converging to something like, okay, 12.13229. For FCC, the same numbers comes out to be close to this one, 12.13188, because FCC and HCP are identical kind of stacking. They have identical kind of stacking. For FCC, the stacking is for FCC it is ABC, ABC, ABC type stacking. For HCP it is AB type of stacking. I hope I have discussed it earlier. Those who have missed it, you can go to the lectures. I have uploaded now those lectures on YouTube, so you can go through that. Or maybe in earlier classes you should have done that. So that is why first term, this is what he's saying. Summation over Pij raised to the power minus 12, sigma over r taken outside. It will be coming in the next expression. So this first term will give you 12.13188. Then second term will be converging because it is raised to the power 6. So if you take 1 over root 2 raised to the power 6, this will be rather small, but not as small as this one, because this is raised to the power 12. So this series will converge to something like this, but both are identical, almost close to each other. Why close to each other? Because stackings are almost very near to each other. Is this clear now?
Yes, sir. Yes, sir.
Sandeep was asking. Okay, fine. Now this is total potential energy. What we have to find out is equilibrium lattice constant. So what is going to be the lattice constant? Lattice constant over which this total energy is minimum, lowest. Lattice constant is the distance or the lattice, the value of interparticle separation at which the overall energy of the system is lowest. So how do we find out? So that can be obtained by taking derivative of, so I'm sorry, I have not put the expression of this one. So this U total will be what? U total is going to be 1 by 2 n 4 epsilon. You can write it like that. This summation or this whole series, first term will be like 12.13188 into sigma over r raised to the power 12, because that's common, right? Minus 14.45392 into sigma over r raised to the power 6. This will be your total potential energy. Okay. Now for this to be minimum, we have to take derivative. So basically you have to take du over dr, and that has to be 0 for overall energy to be minimum. So this factor of half goes to other side when you compare it to 0. All constants will disappear. I mean, we can put them to be 0. In derivative only this will contribute. So what is this 12.13 refers to this value, and this 12 is coming from derivative. So derivative of 1 over r raised to the power 12 will be n into, 12 into sigma over r raised to the power n minus 1. So that is why this 13 here. I hope you know, I'm sure you will be able to do this derivative. So you take this derivative and okay, I give a time to you. I'm giving you some time. You just get it done in your notebook right now and let me know if you are able to get this expression from the derivative. He has retained only first two digits, 12.13, that's sufficient. Okay, 14.45, 14.45. Now you get the derivative and let me know if you are able to get this expression or not. Okay, waiting for your response. Okay, Sakshi says she got it.
Yes, sir, got it.
Deep also got it. Very good. So, it's quite simple and straightforward, but okay, once you do it, you should be more comfortable. Otherwise, it will be like a direct shooting of the final steps. Okay, so this thing put to be equal to 0. So this thing will be going to the 0 side. So this will be 0. This when we simplify, now again I give it a short assignment again to you. You solve it now and obtain what will be the condition. R naught by sigma actually will come out to be equal to 1.09. You check if you can get this thing, you have to put actually to be 0. Then rearrange things a little. You can take help of calculator. Then finally, what the number which you are going to get is this one. Means the equilibrium lattice constant R naught or interparticle separation, you can say, will be nothing but 1.09 sigma. You check if you are able to get this or not. Again, proceed. I'm waiting for your response. Yes, okay. Sandeep says he got it. Others? Harish says he got it. I want to see a few more responses if everybody is able to do this. Diksha got it. If you say you have done it, means I believe you that you have been able to do this. Because otherwise, if something is missing, why I am asking you, if something is missing, I can help you out, do the steps. Maybe if not done today, I can bring those steps done in my next presentation. But if it is done, I believe that you are comfortable, so I won't be wasting time in that. That's what is the point of doing this. So that is what is going to give you R naught over sigma. So now I hope you have noticed that while we were discussing pair potential, what was R over sigma for two particle interaction? That was just 1.12, isn't it? And now when we are thinking of a crystal which is actually made up of so many pairs, means large number of atoms, this value comes out to be 1.09. That was 1.12. Why do you think this decrease has happened? Slight decrease. Yes, let me see your intuitions. How you can think over it. Yes, why do you think this value is slightly decreased? Yes, anyone? Whatever you think. No thinking. See, you think wrong, that is okay. But if you don't think, then that is a problematic thing. So you should think, whatever it is. I mean, there should be some idea. Okay, you should have some explanation to it. Then that may not be right. That is okay, acceptable. But if you don't think at all, then that's something worrisome. Yes, so what do you think? Anyone? Whatever you think. Sandeep, Rahul, Harish, Sahil. Can you hear me?
Sir, due to Pauli exclusion principle.
How will Pauli exclusion principle lead to decrease in this? Okay, fine. That's your speculation. Fine. Anyone else? Rahul, what do you think? What do you think? Come on, no intuition. See, there is something really interesting here. In earlier case, we were considering only two particles attracting each other, right? So that's called pair potential. But now here, we don't have only, I mean, these two particles attracting each other. This particle is also being attracted to this particle, means nearest neighbor interaction is there, and indeed next to next nearest neighbor interaction is also there. And indeed there is not this, these are not just two. This particle is attracted to this one also. I mean, total 12 nearest neighbors, and then next to next nearest neighbors, next nearest neighbors, and so on. So there is some additional energy lowering because of next to nearest neighbor interaction and next to next nearest neighbor interaction, or rather we should say the many body interaction. And due to that, these particles are slightly compressed in comparison to a two particle situation. In case only two particles would have been interacting with each other, they would have rested to each other in such close to each other in such a way that R over sigma is 1.12. But when many particles are interacting, so many particles, so there are next nearest neighbor interactions, next to next nearest neighbor interactions, so that leads to additional compression. And that additional compression leads to this R over sigma being slightly lesser than that two particle case. Is that okay? Okay, so I mean, I assume it is okay. If there is any question on this, I will be happy to answer. Harish. No, as we increase size of the crystal, this factor will decrease. No, I don't think so. I mean, okay, if the crystal is of a reasonably large size, then this factor will retain this value. Why so? Because if you increase size of the crystal, what you are going to increase is the number of terms in the series, and that series, of course, is going to converge to 12 point blah blah blah, whatever it is. Even if you, so increasing size of the crystal is means you are putting more and more neighbors, but not nearest one. You are putting more and more neighbors of an atom which are at far away distance. So far away distance neighbors doesn't contribute anything to the series. So nearest neighbor, next to next nearest neighbors, all those are going to remain same. Increasing size of the crystal will only increase the far away neighbors, which doesn't contribute anything significant to the interaction. So that's okay. I mean, yeah, there is interaction due to nearest and next nearest neighbors and others which are at reasonable distance, which can lead to, which do lead to compression and hence decrease in this value. Okay, fine. Is there any other question from this part? I mean, this thing which we did. Any question?
No, sir.
Okay, you also all, I mean, sign your attendance. Let us proceed further meanwhile. So these are the values. So this is a theoretically driven value as per this thing. We use Lennard-Jones potential. So this gives us the value, which should be like this one. But then experimentally, it was found that this R over sigma for neon comes out to be 1.14. Now you will ask, okay, then that 1.12 was really better, huh? Means neon must be following that pair potential. No, that's wrong. So this is not because of that. I mean, bare potential is always the same. I mean, you should not give stupid reasons for this. So the reason for this value being close to 1.12 is something else. Yes, then argon. Then you will see that xenon is something which is nearest to this one. Means xenon seems to be best following this. So what do you think? Again, let me ask you. What do you think about this? I mean, why is xenon being really close to 1.09 and why this deviation? And this deviation is increasing as you are going towards neon. So you are moving to smaller and smaller atom, the deviation from this value starts increasing. Why so? Any guess or any speculation, any intuition? Have anybody heard of it or studied it earlier? So the reason, okay, the slight departure of this from this is actually because of quantum effects. This can be explained on the basis of 0-point quantum effects. Now question is, okay, what is quantum effects? Why they are maximum for neon? Why not for xenon? Isn't it? These are the questions which follow. So, okay, let's come to the next slide for this. Has it been given here? I didn't give it. Okay, it is in the next slide. Fine. So those quantum effects are explained here actually. That okay, the quantum correction comes here. So we can relate quantum wavelength or de Broglie wavelength inversely proportional to mass, right? So neon being lightest as smallest mass among all, and hence has largest de Broglie wavelength. So larger is the de Broglie wavelength, more prominent will be the quantum effects or quantum correction. That's why the quantum correction is highest for neon and hence deviation is also highest, and quantum correction is lowest for xenon because heaviest of all, hence the correction is least for xenon. I hope that's okay. Then comes the cohesive energy. What is cohesive energy? Is cohesive energy of a crystal is defined as energy that must be added to the crystal free atomic form at rest at infinite separation with the same electronic configuration. I mean, they are in neutral form, so whatever is their electronic configuration, they are brought back to that. Or conceptually, what it means is cohesive energy is the amount of energy which must be supplied to a crystal in order to break it completely and take the constituent atoms of the crystal far away from each other, so that those atoms are not at all interacting with each other. I mean, you break it completely. It's like crystal is broken back to its reactants. Another way of looking at cohesive energy is, okay, it is the amount of energy which is released when a crystal is formed from its neutral free atom reactants. So if you're saying sodium chloride crystal, if you want to talk about cohesive energy, means you take sodium neutral atom, chlorine neutral atom, take one electron from sodium, the energy cost for that, add that electron to chlorine, the energy released in that, ionization energy and electron affinity, then take those atoms close to each other. The amount of energy, net energy released in that whole process is actually called the cohesive energy, okay? So we can calculate the cohesive energy. So basically cohesive energy can be calculated by putting this value, because this is the equilibrium lattice constant. So you are not total, when we put R is equal to R naught, then we can calculate the cohesive energy. So we just have to put the values here. Then cohesive energy turns out to be equal to 2.15 into 4 N into E. E we know from the table. I think I had shown a table in the previous slide somewhere here. Yeah. So here is your E. Then you can put that and then write down the expression for that cohesive energy of noble gases. So this is the table not only for noble gases but for all the elements in periodic table. This gives you the cohesive energies. So here is this is taken from Kittel's book. This is in, so these values here are in kilojoule per mole. These are electron volt per atom. The gray, the values highlighted in gray. Let us follow one particular set of values, say electron volt per atom. So if you see the cohesive energy for something like carbon in diamond structure, then that is something like 7.37 electron volt per atom. Now you can compare the cohesive energy of neon in comparison to carbon. And neon cohesive energy is very, very less, 0.02 electron volt per atom. So now from here you can guess how weakly these inert gas crystals are actually bound. And this of course is so because the force which is holding them together or binding them together is very, very weak, Van-der-Waal interaction. So that is based upon weak dipole-dipole interaction effect, and that can't be very, very strong. So that is why these crystals are weakly bound. But yes, if there is a binding force, that can lead to crystallization. So you can see for neon it is 0.02 EV per atom. For argon it increases slightly, not slightly, I mean 0.02, 0.08, almost like 4 times. Because if you substitute those values, the values comes out to be correct. 0.116, 0.16, and so on. So that is how we can understand cohesive energies of inert gas crystals. And then I already told you quantum mechanical corrections. So that's okay. Heavier the atom, smaller will be the quantum correction that we discussed. Okay, that's all for today. I mean, that completes our noble gas crystals, or the crystals interacting via Lennard-Jones potential. If there is any correction, any question from this part, I will be happy to answer. Otherwise, in next class, we will be talking about ionic crystals. So these were like Van-der-Waal crystals as of now. And then next will be the ionic crystals. So is there any question from Van-der-Waal part or inert gas crystals?
No, sir.
Okay. Anyone else? So you got everything? Then that is really great. If I could teach you each and everything correctly, that's nice.
Yes, sir. बहुत अच्छा था आज का lecture.
But I don't know it was really that great or not. I mean, at least MSc students, आप लोगों को सब समझ आ जाता है क्या, या मतलब कुछ कुछ समझ नहीं आता है और आप चुप बैठे रहते हो? Yes, my young colleagues, I mean MSc fellows, do you get everything, or you just keep on sitting silently and hoping that okay, we'll do it ourselves later on?
80-90% समझ आ जाता है.
Oh, very good, Kush. Nice. So 10% में क्या नहीं समझ आया? You can ask from that 10% also. I mean, make sure that you understand everything. I mean, even if there is any kind of question can be anything. So you feel free to ask questions so that you don't miss even that 20%. Okay, any question? Final call for questions. Out of even that 20 or 10%, any question if you would want to ask? We don't have time. Okay, don't feel that okay, I will waste your 10 more minutes. I can answer your questions in next lectures also. I know we are running out of time, so you put your questions here. I can answer it tomorrow as well. No issue. Nothing? Okay, fine then. Thank you.